For me, the story began in '88, or actually '86, I'm sorry, when Alex Miller came to the Ghana. He showed this picture of polarons as being responsible for high temperature superconductivity. It's a chain, a bit like a polymer with a distortion and so on. And he was very convincing. At least I was really convinced that this was very important and interesting. And luck would have it that I got a scholarship, but I really wanted to study polarons experimentally. This was back in '88. Where the best place one could do experimental studies of polarons was of course, in Santa Barbara with Alan Heeger. Here's a paper at that time which showed a hump which was sort of somehow attributed to polarons in cuprate superconductor. Now, great. So Alan was very kind to take me on. So I spent a wonderful year at Santa Barbara. And basically did some theory and some experiments and ended up with showing that polarons indeed are quite common in oxide materials. Now, this is a nice paper that's actually quite got a lot of citations or interest later on. Now, Alan, I think probably wisely left the field for a while, for more or less. I think that at the time we were quite disappointed that the community wasn't very excited by all this work. Right? Somehow the polaron picture didn't catch on, and there were other ideas which were quite different, didn't involve lattice at all, and more spin related. But let me just fast forward to a couple of years ago. Just a simple observation, which I think would please Alan, and that is that look at this. This is an old-fashioned spectrum which I showed you earlier, right? Back 30 years ago almost. What you see, and that was done in a very slow experiment, and there was always a criticism that maybe some of this is junk, right? Carriers get trapped in some junk states and so on. Well, here's an ultra-fast absorption spectrum. It's exactly the same shape. Right? So basically, a femtosecond spectrum is the same as a millisecond spectrum, which means that basically the thing is intrinsic. There's a polaron which is intrinsic. Okay. So where did the other guys do? There was all these strongly correlated physics, TJ models, Hubbard models, and so on of high TC. Well, actually, the best they could do was somehow find that a polaron forms very quickly on a square lattice, which is very nice on the order of femtoseconds. But it's really not, so this is what I'm going to talk about, how that might actually, a more realistic physics might occur. And then I'll talk about another subject, which is very recent, very exciting for us. It's created a lot of commotion, and I hope it will do with you guys as well. So the first question is how to deal with polarons in 2 dimensions. As I said, we have an inorganic crystal. Ignore the chemistry. It's really not relevant. We have polarons, okay? So you can discuss the displacements and so on, but this gets very complicated and messy. It's very material specific and very unsatisfactory. It's not like the beautiful polyacetylene or polarons models on conducting polymers. But on the other hand, here is a picture of an STM picture of polarons of charges localized on a square lattice. That's actually a typical cuprate. So how do you deal with that? Actually, this is that's the best you can do with Hubbard or TJ models. So, but these models actually miss out on the symmetry aspect of the problem. So in 2 dimensions, you already have another variable, and that's symmetry. That's the symmetry of how the polaron states are constructed. And this is just a brief point. This is a square lattice. If a polaron is localized between 2, on this point, this is an oxygen between 2 coppers, you can either have it this way or that way. Okay, there's already 2 different states, and that relates very nicely to the original idea, at least in concept of the antellopolaron of Alex Miller. Now, I'm just going to very briefly show you what you can do with this kind of model. If you just take a strain, just like you do in a polymer, right? So it's the strain energy, and write a Hamiltonian with a strain and a Coulomb repulsion between the 2 charges. And you'd have the option of it going this way or that way. That's all I'm putting into this model. It's a very, very simple model. In fact, what you turns out, you can do a Monte Carlo calculation, which is common for these things, and you get these kind of different patterns, and you see that two things I just want to notice. First, there's a symmetry here. Depends on how you arrange this interaction symmetry, and that looks very similar to the experimental observations up here. And the other thing I'd like you to notice, for a certain relatively large level, set of doping levels, you get pairs. Now, pairs are bipolarons, and bipolarons are bosons. So there's a very simple superconductivity model. Here's the, hopefully that, so this is the Monte Carlo calculation. The red actually are up, and so these are the red and green are the two orientations. As you cool down the temperature, basically you get percolation of these pairs, and at low temperature, essentially, you can get a percolating state if you're lucky, and that is the phase coherence percolation. Now that's a model which is showing, this is the phase coherence, this is the phase diagram that one obtains from this. Okay. Okay, this is just a one, I'm not expecting you to go into the detail or to understand the details, but it's just a demonstration of what happens when you have two-dimensional models. So, and just to conclude this part, introduction, actually, since other models of high-temperature superconductivity have sort of run into difficulties in the sense that they haven't really explained anything or predicted anything, it's rather satisfactory to, I think both Alan and I, we should be happy that in the most recent handbook on high-temperature superconductivity in 2016, Alex Miller proposed in the introductory chapter that polarons are responsible for high TC. So maybe you should have stayed a bit longer. Anyway, okay. Let me now change gear a bit. And I'm going to talk about another kind of polaron ordering. It's still in a two-dimensional lattice. And I'm going to do experiments in time. Now, what does that mean? Most people do phase transition experiments by changing temperature, pressure, whatever, magnetic field, something or other. You basically go through a phase transition. Now, just to be different, we decided to try and do this in time, okay? Now, why is that interesting? Generally, it's interesting because actually some of the most important transitions that we care about happen in time, like the Big Bang and collisions in the LHC between protons and antiprotons, and also stock market crashes or phase transitions in time. So let's study that in our model systems. Now, okay, how do we do that? It's very straightforward, actually, conceptually. Imagine any kind of system that you can somehow study optically, right? And what you do is you have one short pulse which basically heats up your material or forces it somehow into the non-ordered state, okay? So that's the first laser pulse. It's sort of blue, okay? It impinges on the crystal, and the other two are basically doing pump probe spectroscopy, femtosecond spectroscopy, which is designed just to test how the system is evolving after you've really disturbed it by the first pulse. Okay, conceptually that's quite straightforward. Okay, time resolved spectroscopy as the system is evolving in time. Okay, that's a rather new way of doing things, but it tells us rather new things. So there's two reasons why this is interesting at the moment, and why we're particularly interested in this kind of work, is that actually back in '82 there was we were actually interested in metastable states, and this is the paper by Frank Wilczek, actually in Santa Barbara at the time, who suggested that, well, maybe our universe is actually metastable. And essentially, he proposed with Michael Turner that we are sitting here in a metastable potential. Okay. Now this is very nice and theoretical, and it didn't really attract much attention. Okay. But it turns out that later on, people calculated what are the parameters for that potential, and the two parameters which determine whether we are in a metastable universe or not are the top quark mass and the Higgs boson mass. And both have just recently been measured. And with a confidence level, which is given here, it turns out that we are in a metastable universe. So, okay, that's according to the model, of course. It's the standard model. It's the so on and so forth. But what we are interested in is actually looking at phase transitions such as this one in time in things which have a metastable state. That was our original hypothesis. And our model system is going to be a two-dimensional polaronic crystal with the appropriate symmetry so that it has a metastable free energy. Okay. Now, there's another reason to study this, and that's a very practical one, and that is, of course, that metastable states imply memory devices. Now, here's the two most important and basically world record achievements. One is the currently record write time, which is 500 picoseconds in a PCM device, which essentially does a structural transformation. And here's the energy per bit. Okay, it's all over the place. I'll get back to these diagrams at the end. Okay, so our system is a hexagonal polaronic system. Now, there's no time, or it's not really the occasion to go into detail, but let me just tell you a little bit about why this is so. We're using tantalum disulfide in this polytype form. So basically, this is a nice layered material which is uniform or metallic at high temperature. As you cool down, essentially, it forms these beautiful waves, charge density waves. Now, as you cool down further, these what you call domain walls disappear, and you get a beautiful hexagonal array of polarons. Now, the good thing about these materials is that you know, because these things, polarons are ordered, you can tell the position of every atom, the charge on every atom. You basically know everything about this polaron, the displacements and the charge, okay? And in fact, they look like this. So each one of these, this is an STM picture, by the way. You can see these hexagons. This is Star of David, in which 12 tantalum atoms are essentially displaced towards the central tantalum atom, okay? And this forms one polaron. That's a fact, experimentally measured by X-rays, electron diffraction, anything you want. So essentially, this is the lattice that you have, okay? And as you go through these transitions, the resistivity shows also nice jumps, basically going to an insulating state at low temperature. And what we're going to do is we're going to start with this low temperature state and try and change it somehow with our experiment. So just a note for consistency, it's the hexagonal structure which allows us to have a third order term in the free energy, if there's some theorists around you here, and that basically gives you a metastable state. Okay, so how do we do this? Here's the experiment done by Ljubka. This is essentially what happens after the first laser pulse. The reflectivity of the material changes, oscillates as you have excited this polaron breathing mode. Okay, it's like a reflectivity effect. Okay, now there's no need to worry about details. Let's just take my word for that. Now, after I put an intense pulse, you remember the one that was supposed to change things, okay? You see that the spectrum changes, okay? All right, maybe we burnt it, the sample, maybe we melted it, we've done something funny to it. No, actually, it turns out we haven't, because if we just a little carefully heat the material with another laser pulse, we recover exactly the original spectrum. You see, the green and the black are so right on top of each other, it's almost identical. So basically, we have a reversible change in the material, in the optical response. Great, fine. This could be anything. Well, the obvious thing at the time was, well, maybe we're inducing a new state, which is different, this red thing, and maybe it's superconducting. Photo-induced superconductivity has been another common interest, I think, with Alan. Now, okay, so Heeger did the obvious thing, put contacts on it. It took a while to do it right, but eventually we found that, indeed, after a single 30 femtosecond pulse, the resistivity changes by 3 orders of magnitude. Unfortunately, it doesn't go to 0, a bit to a disappointment, but nevertheless, here we are. And as you go heat it up again, it recovers and eventually joins up with the usual state above at high temperatures. Okay. Now, what's particularly interesting is that all this can only be done with very short labors of pulses. You can't do it with long pulses, and that's related to the mechanism, but I don't have time today to go into detail. So what is happening pictorially? I can explain it relatively simply. Imagine that you have a hole. Imagine that the electron is held up somewhere in the relaxation process. Basically, after photoexcitation, an electron is stuck somewhere trapped, okay? And so what we have is a hole, and this hole annihilates an electron in the middle of one of these stars of David. Okay? It creates these polaronic voids. So these are polarons, and these are voids. Now, as you proceed to do this in time, these voids like to order and form essentially an ordered state. Okay? Now, in terms of energy level diagrams, here's a very simple picture. First here, it's an insulator. Remember, I told you resistance went up at low temperatures, and with a gap, and the gap is closed in a fashion which is actually with another friend, Sergei Brozovsky. The theory was we developed a theory. Essentially, it's a polaronic concept of conversion from polaronic to itinerant states. Okay, so essentially what we're creating is another ordered state here, which with some pattern. Okay, now that was published in this paper 2 years ago, and since then we did the obvious thing, and that is to look at the crystal structure, the STM images of switched crystals. So remember the one that I showed you earlier? It was nice and uniform. There's basically polarons beautifully in a hexagonal pattern. Well, here you see exactly the sort of features that we predicted in our original paper, which we were, I must say, very happy about. That you actually see that at different temperatures, right? Eventually, it melts at 200 Kelvin or so. This order melts, and that's it. So basically, with a single laser pulse, 30 femtoseconds, we're changing the material. We have a metal insulated transition. The resistivity changes by a factor of 1,000, and we have essentially an ordered polaronic crystal. Right. Here's a beautiful, the reverse process. If you spontaneously leave the material, it will actually relax. And here's the, if you notice these features here, it doesn't relax one polaron at a time. It relaxes one line at a time. And this is related to topological protection. In other words, there's no single particle excitation that can relax your polaronic crystal. You have to relax the whole line. That's a question. That's a topological argument. So, how much time do I have? It's over. Okay, very quickly. I'll skip this one. Just on the application side, well, if you can do it electrically, that would be even greater. Then you can do it as a memory. Here's a demonstration. Actually, it was a clever idea by Ian. He came up with the idea of using an optical pulse to generate an electrical pulse, and that electrical pulse switches this sample, this crystal here, and it works exactly the same way as with optics. And here's a nice little, in the next slide, I have a nice little movie. Hopefully it'll show, how this is happening. Okay, essentially, as you apply a pulse between the electrodes, it converts it from a uniform polaronic crystal to a patterned, textured polaronic crystal. Okay, and now to finish off, it works also with Z-axis. This is a technologically very important issue. It doesn't matter whether you put contacts like sideways or on top of each other. That's very important technologically. It works both ways. So here's a news feature from just a couple of days ago, I think. Intel insanely fast 3D X-point technology hitting high speeds next year. A test showed operating at 7 times the speed of fast NAND flash parts. Okay. Now, I'll put that on a diagram. So here's the current technology. This is 7 times better is here. This is the PCM paper that I mentioned in my introduction. Remember there was a picture. And this is our electrical switching, and this is our optical switching. And the beauty of this is because the whole thing is totally electronic. There's no lattice rearrangement, recrystallization, ion motion in this process. It's all totally electronic. The energy required to switch is tiny. So essentially, we are here at the moment. This is our current device size. And of course, the lower the better. And this is the theoretical region where we expect with smaller device sizes. What should be? So, I think here's an appropriate slide to end with. Okay, so happy birthday, Alan. I think you've got more than just conducting polymers to hang on your belt or under your belt or whatever. And I think I'm grateful for all the wisdom and the, how shall I say, inspiration that you've given me and all of us in all these years. And it's been a great pleasure and an honor and a privilege to have known you, or to know you. Sorry. So, thank you.